definitely prove to be a triggering agent to the various to further motivate the young people in colleges and the university. And I salute to the organizer that in the colleges where we have lots of problems, we do not have proper infrastructure, we do not have the very typical. Even then, they are organizing this conference, to come meeting, inviting the new ideas and discussing these new ideas in the field of the physics. So I congratulate all of them. I wish all the best for the grand success of this conference, and uh, I inaugurate the conference for the benefit of the society. Thank you very much.
Thank you, Professor Chandolaji, for your thoughtful address. It is now my pleasure to introduce you to our chief guest, Professor Sachin Maheshwari. Professor Sachin has done his PhD from Mechanical Engineering Department, IIT Delhi. He is working on an arc welding, hardening of steel, matrix composite, and published several research papers in this field in national and international journals. Currently, he is professor and head of Department of Manufacturing Process and Automation Engineering at Netaji Subhas Institute of Technology, New Delhi, and also as a dean of Industrial Research and Development. Now, I will invite Professor Sachin ji. Sir, Sachin sir. I think Sachin sir has left.
Good morning to all of you. Am
Good
I audible?
morning. Yes, sir.
Yes, yes.
Uh, well, thank you, friends, for inviting me to a physics conference. It's little unusual to be invited in a physics conference, a mechanical engineer being invited to physics conference. However, I readily accepted the invitation because one, it is rare, another, that it uh, gives you a platform to express your thoughts. And a teacher would always love to express his thoughts as and when these are solicited, and even when these are not solicited. Uh, the International E-Conference on Recent Advances in Physics, a promise to society. The word promise is very catchy. Uh, why we need to make promises at this juncture? Because we are going through a very torrid time. It is a very difficult time for us, both because of the pandemic situation and because of other geopolitical situation, and because of the situation for that we only are responsible. That as far as I can say, technologically, because I am a student of engineering, that we have not got the respected place which we should have got. I would not say at this juncture that we deserve that place, because our ancestors might have deserved that place, but we don't. Uh, Today, because of all these things, we are the largest technology importing nation. So that is why, as Indians, we have to make a promise to the society. So that is why I say this promise is a very catchy word. Today are the times when nation requires several true promises to be made by us. So a guest speaker, my job is to enthuse you so that you not only make promises but also keep those promises. Basically, I'm a student of engineering, as I said, and that is why I consider myself not an outsider to the physics fraternity, as physics is mother of all engineering. And a physicist promise has to be carried out by an engineer, because applied physics is nothing but it has to have some kind of engineering element. So it is like a Krishna Arjun relationship, when vision and action both are important, and but in isolation both are waste. So what we need is not only a vision but also a program of action. And mere vision can be a daydreaming, and mere action would be a waste of time. So if you have I don't know if somebody has read Bhagavad, the last slok of Bhagavad mentions Yatra Yogeshwara Krishna Yatra Partho Dhanurdhara Tatra Shri Virjayo Bhutidra Neter Marti Termama. This means that the Purna Purushottam Bhagwan Krishna, he represents the divine vision, but the vision alone will not help. And on the other hand, the Parth, the Arjun, the archer, is the man of action. So without vision, he cannot achieve success. So both have to work in tandem. So, well, friends, a promise is a promise, and people with good intentions make promise, and people with good character keep them. So I hope during these conference days, you are not only going to have good intentions by making good promises, but also you would be in possession of good character to keep them. Why I am emphasizing on why I am having a little suspicion that we are not able to keep our promises, though I pray to Almighty that this conference would be an exception, and where most of the promises are to be kept, because we have not been able to build quality institutions, and quality institutions is about people. We have to have hungry students and hungry teachers. The hungry, we are blessed that because of our demographical dividend, we are blessed with the hungry students, and but hungry teachers, it's very difficult to find. So it has to be, because teaching profession should have been a most compelling profession in society in every sense, in its richness, in its experience, in its conversation, in its freedoms. Teaching and research both. These professions should have been like that. And in ability should have been in abundance. Not to mention compensations. So only the best can bring these institutions back from the brink. Why I am saying brink? Because we can be proud of our heritage. We can be proud of our past richness as far as science development in sciences was concerned.
Yeah.
Bhuvesh sir, he is not audible.
Okay, I think Sachin sir has disconnected. Okay, let's proceed. I think I have to wait. We have to wait. Okay, let's proceed to the next session. Where is my camera? Okay. Now let's proceed further. Thank you, Professor Maheshwari. And you are right. Physics and engineering both are related to each other in many aspects and has very important role for our society. Now, I will ask Professor S.V. Chandola ji to declare this conference open. Sir, Chandola sir.
Yeah. Am I audible?
Yes, sir. Yes, sir.
Can you hear me?
Yes, sir.
Can you hear me?
Yes, sir. I am.
Okay. So the conference is open now to all the contributors and participants of the international conference. Yeah. So should I call the first speaker?
Yes, sir. Yes, sir. It's like down time.
Okay.
It's time for our keynote lecture.
So sound is not clear?
Yes, sir. It is coming.
Wait a moment. Yeah. Is it okay now?
Yes, sir.
Am I audible now?
Yes, yes, sir.
Okay, so thank you, Bhuvesh, and uh, can you listen me?
Yes, sir.
Okay, am I audible?
Yes, sir, sir. All are mute, sir, right now.
No. My voice is there.
Sir, your voice is there. Yes.
Okay. We now start the conference. The main agenda of the conference. That in this first session, I'm thankful to you that you invited me to chair this session. And in this session, in this conference, recent advances in physics, a promise to the society, 2020. I invite Professor N. Nimai Singh. I would like to introduce Professor N. Nimai Singh. He will deliver his talk here. Professor N. Nimai Singh, he comes from Department of Physics, Manipur University, Imphal. He has been ex-head of the department and convener of the physics department at Manipur University during 2017 to 20. And he was at the Guwahati University also as a head of the department from 2010 to 2013. Professor Nimai Singh has done his PhD from Delhi University. He was after his PhD from Delhi University, he joined as assistant professor at the Guwahati University in 1991. Professor Nimai, please correct me if I am not correct. Yeah, thank you very much. He has been a recipient of Commonwealth Fellowship in United Kingdom during the year 1999. 2000. He has been a regular associate of Abdul Salam International Center of Theoretical Physics between 2003 and 2010. He has been General Secretary of Physics Academy of Northeast, PNE. He has been founder member of the Research Interest of Science and Technology, RIST, Imphal, and he is actively engaged in popularization of the science. We salute to Professor Nimai Singh for his endeavor. His fields of interest are high energy physics, theoretical, of course, the quark dynamics, the grand unified theories, neutrino physics. He has published a number of papers in international journals. He has produced more than 15 PhDs. He has written a very nice book on quark model and beyond, The Eternal Quest. I'm right. With this brief introduction of Professor N. Nimai Singh from Manipal University, Imphal, I request him for his keynote address. His topic of the address will be neutrino oscillations and some unsolved issues. And he'll be talking in terms of for Super Kanya-Konde detector for neutrino oscillations, which has got Nobel Prize in 2015 for the neutrino oscillations, right? So thank you, Professor Nimai Singh, for your contributions and accepting the invitations for this international conference. And I invite Professor Nimai Singh for his deliberations. Thank you. Professor Nimai Singh, I think your mic is muted. Yeah, can you please unmute your mic because you are not audible. Your mic
right,
is.
You're right.
Thank you.
Yes, okay. Can you hear now?
Yeah, I can hear that.
Okay, should I start now?
Yeah.
Yes.
Start.
So first of all, I am very happy to express my feelings that I am able to interact with all the experts here, and I am very thankful to Professor I.C. Chandola and Professor Sachin Maheshwari and convener Aadarsh Kumar Chaudhary and his team. And now I will start directly, and I also thank all the participants of this conference, beautiful conference, international conference, recent advances in physics, a promise in society. Even though I speak on theoretical physics, theory and experiments are related to this. Theory is tomorrow's experiment. So please bear this thing. Okay, let me start directly. Can you see now? Hello?
Are you sharing now?
Yes, I am sharing. You can see now?
No,
Hello?
no.
No, sir.
How to share?
Please
Sir,
open
there is
the
a
option.
Oh, now I will do present now. Okay, I will click on present now. Present now. Okay, okay. Share. Okay, okay, okay. Okay. Can you see now? Hello. Can you see
Yes,
my slide?
Yes.
So now
Thank you.
I will start. This is my first time in e-conference. This is why. Okay, please excuse me. Okay. So today I am speaking on neutrino oscillation and some unsolved problems. Okay. So to start with, when we talk about physics, we have three things. That is our mind, consciousness, and the physical world. That we have to understand what is the physical world. Apple falling is the physical world. After that, in order to explain the physical world, we should have the mathematics. Whatever things we have in physics, we should be able to explain with the help of mathematics. So mathematics is the language of physics, and the mind, physical world, and mathematics is called eternal triangle. So it is a synergy. Okay, that is what I believe. Then the next step is I just want to summarize the development of the physics. When we have a cube, this is cube of nature. When we have a cube formed by three constants: gravitational constant, Planck constant, and the velocities of light, the starting point 0 is called the Galilean physics. Here there is no gravity, no quantum mechanics, no relativity. This is called the Galilean physics. When this Newton's gravity and the special theory relativity mix up, we call another theory called general theory of relativity, which does not have quantum mechanics, but it has gravity as well as relativity. On the other hand, in the 21st century, when there is a myriad of quantum mechanics and relativity, we have a new theory called quantum field theory. Quantum field theory, we don't have gravity here. Neutrino physics will come into the quantum field theory. But everyone knows that a true theory of nature should encompasses gravity, relativity, and quantum mechanics. So people are looking for this theory. So far we have the theory called superstring theory. This theory, we suppose that it can explain gravity, quantum mechanics, and relativity. So this is a brief idea how the conceptual development in theoretical physics occurs. This is we call the cube of nature. Now, before I start my topic, let me point out that in the last 50 years, all the major branches of physics in the basic sciences, they merge. Particle physics and accelerator physics, general theory, relativity and cosmology, space technology, astronomy, planetary science, so Hubble telescope, NASA, COBE, WMAP, LISA, Planck, these are satellite. Biology, origin of the life, computing, electronic, mathematical science, data-enabled science, big data, computational physics, artificial intelligence, physics. And so these are different branches. These branches are interlinked. These the connectivities of the major field of studies. For example, particle physics is related to the cosmology. When we talk about the cosmology, the Big Bang theory, we have to explain through particle physics. These are related. Similarly, cosmology is related to space science. So in order to study cosmology, we need space science. In order to have space science, we have the computation and robotic. So in order to have the origin of life, we should have the quantum mechanics. This is anthropic principle initiated by Schrödinger. So genome, in order to have the genome problem, we have to have computation. So these are interlinked. So what I want to say that in last 50 years, all the major field of studies are connected. So in one way, there is separate branches of physics. All the physics branches will be connected one another. So this is called the connectivity of the major field of the 21st century. Okay. So this is a brief map about what we know, what we are going to do. So say quantum, so there are many places where they have matter, antimatter, asymmetry, this grand unified theory, M theory, superstring, the higher dimension. So these are the places where we have to find out. These are places we have to find out. So this is a brief map about what we have done and what we are going to do in physics. Okay. So coming to neutrino physics, let me point out some puzzle from heaven. So now we know the Big Bang theory, but what is the origin? What is the mechanism for the origin of the Big Bang theory that we are still looking for? So then just after the Big Bang, there is the inflation. What is the mechanism of inflation? That is we are looking for. Then antimatter matter asymmetry of the universe via CP violation. That is we are working for, we are looking for. Nowadays we have very high 10 to the power 19 electron volt cosmic rays. From where these cosmic rays are coming, how they are formed, it is a puzzle now. We have dark matter. Dark matter, as you know that it is which cannot be seen by telescope, okay, but they have the gravitational pull. Dark energy, which have an anti-gravity effect, which help in the expansion, accelerated expansion of the universe, and the solar and atmospheric neutrino physics, gravity wave. This is the area where I am going to emphasize, and these are related with all these things. Okay. Now we know that the universe is more than around 70 to 75% are the dark energy that is anti-gravity effect they are having, and they are a pervasive medium. Okay, they help in the accelerated expansion of the universe. Around 27% is the dark matter, which we cannot see by our telescope, or okay, they are immune to light. They are chargeless. Okay, 30% is our ordinary matter. That is we know already. So this is another graph. Now, when I talk about the new physics means which is beyond the standard model of particle physics. Standard model means electroweak, symmetric, electromagnetic, weak, and standard strong force. These three unification is called standard model of particle physics. What is beyond the standard model, we call it is the new physics. Neutrino physics is neutrino mass is new physics, dark matter is new physics, dark energy is new physics, supersymmetry is new physics, proton decay is new physics, string theory is new physics. So my topic is neutrino physics. Now this is the famous graph of Vera Cooper-Rubin and her collaborators to find out the existence of the dark matter. It is the rotational galaxy. Experimentally, it should be done like this. Theoretically, it should be done. It is the experimental. It means that far away from the galaxy, center of the galaxy, we have a lot of matter called dark matter. Okay, that is the famous M33 rotational curve of Vera Cooper-Rubin, who died recently in the last 1 year. This is the famous picture of WMAP where there is the accelerated expansion of the universe. This is the inflationary, the accelerated expansion of the universe because it was given the Nobel Prize. Okay, so we are going to find out the existence of dark energy for the accelerated expansion of the universe. Still, we are going to find out, but for this observation, Nobel Prize was given. Okay. So now, in this talk, I am confined to neutrino oscillation. So to start with, let me start from the 2015 Nobel Prize in Physics. 2015 Nobel Prize in Physics was devoted to two persons. One is Professor Takaki Kajita and Professor Arthur McDonald. So these two, Professor Kajita, the Japanese fellow, he was the leader of Super Kamiokanda in Japan for the discovery of the neutrino oscillation, atmospheric neutrino oscillation. And Professor Arthur McDonald, he's the leader of the Sudbury Neutrino Observatory SNO in Canada. So the implication is that neutrino can oscillate between the two species, from electron neutrino to muon neutrino, from muon neutrino to tau neutrino. In ordinary physics, standard model physics, they cannot oscillate, they cannot change. But here, it is found that they oscillate. This is why it is beyond standard model. It is the new physics. This is Professor Kajita and Professor McDonald. Okay. So, as I told you, in neutrino oscillation, from one flavor to another flavor, it is a quantum mechanical superposition when the neutrino travels, it pick up a phase. Okay, a phase. So it is the quantum mechanical superposition that I will explain in future. Okay, so neutrino oscillation is one of the hottest topic in physics, both from theory and experimental front at the moment. Okay. Okay. So now the significance. Now the neutrino oscillation is so. Hello, can you hear me?
Yes, yes.
Hello?
Yes.
Yeah, okay. There is some. So now the neutrino oscillation is the example. Neutrino oscillation, there is the vibration of electron number conservation. In neutrino oscillation, there is a electron number conservation. Okay, that is beyond standard model. So in neutrino oscillation, there is vibration of CP vibration also, and it may explain the matter-antimatter symmetry of the universe. Okay, so
Nimai sir, you are not audible. Your mic has been muted. Nimai sir, Nimai sir, voice on.
Please unmute your mic. Yeah? Mr. Nimai, please unmute mic.
Presenting. Yes, can you hear now?
Yeah.
Okay. Okay. So now, what I want to, can you hear now, please?
Yeah.
Okay. So now, if this in this neutrino oscillation, if lepton number is violated, there is a possibility that neutrino may be Majorana particle. Majorana particle is particle and antiparticles are the same. Okay. So this is the classification. We know that. So we have fundamental forces means those vector bosons, leptons, and quarks are the fundamental particle. Okay, fundamental particle. So we have neutrino. Okay. So this is the fundamental elementary particle. We have 6 quark. We have 6 leptons, and this neutrino, we have 3 neutrino, 1, 2, 3, electron neutrino, muon neutrino, tau neutrino. This is the chargeless lepton. Okay, so they are massless in a standard model, but others are having masses. Okay, so in brief history of neutrino, we know already. I will skip. It started from James Chadwick in 1914 because neutrino beta decay should be a continuous. In order to explain the continuous, we have brief neutrino history. We starting from Wolfgang Pauli, Enrico Fermi. We have in 1956, neutrino was first discovered, electron neutrino, antineutrino. In 1962, muon neutrino was discovered. So in 1968, so in 1987, neutrino from supernova were detected. So in 1998, okay, the atmospheric neutrino oscillation by superconductor were confirmed. Okay, so in that way, in 2002, okay, so this is the history of neutrino. So now this gentleman Joji Totsuka, he was the leader of Super Kamiokanda, but before announced before getting Nobel Prize, he was dead. So he was replaced by Kajita. Okay, so now another hero is called Bruno Pontecorvo. He proposed the neutrino oscillation. So in 1957, Bruno Pontecorvo suggested the neutrino oscillation, and it was extended by Maki, Nagagawa, and Sakata. So this is then it was modified by Gribov, Wolfenstein, and Mikhail. This is we call MSW effect. Okay, this is solar neutrino. So when we talk about the solar neutrino oscillation, we call it is MSW effect, because when neutrino come out from the sun, it interacted with the electron gas, and it gives the maximum neutrino oscillation, maximum mixing. Okay, that is called MSW. We call MSW resonance effect. Okay, so let us come to the neutrino sources. So when we discuss about the neutrino, in Big Bang theory, we have a large number of neutrino. Like cosmic microwave background, we are believing that there is the neutrino microwave background, neutrino background. So it will give, study of neutrino will give the understanding of Big Bang theory. Solar neutrino, because sun produces through thermonuclear reaction, by thermonuclear reaction, okay, by fusion of proton, it makes helium nucleus, and finally it produces neutrino with the energy about 26 MeV. So it is solar neutrino. From supernova explosion, it also gives neutrinos. The energies are different. Okay, we have atmospheric, from atmosphere, from cosmic ray, finally from cosmic ray, finally we have electron neutrino and muon neutrino. and from high energy cosmic ray 10 to the power 12 to 10 to the power 19, okay, electron volt, cosmic ray sources, neutrino from the earth inside also. So nowadays, in order to investigate the geological investigation, we use neutrino because neutrino can penetrate inside the earth. Okay, so these are the sources of neutrino, but artificially we can also create accelerator neutrinos. We can create reactor neutrinos. These are the different sources of neutrino, and we have different energy for these. Okay, and we have different energy. So let us come to so my timing is off. Should I continue for another 5 or 10 minutes? Hello, hello, hello.
Hello.
My timing is up. Should I continue for 5-10 minutes?
3 minutes, yeah.
Okay. So
Thank you.
Okay. So it is the beta decay. It is the beta decay. So we have, this is for quark part CK matrix. This is the quark. This is the neutrino part called PMNS matrix. Okay. So I will jump about. So it is the theory of neutrino oscillation. In order to have a neutrino oscillation, we have the this is called we eigenstate. Nu1 and Nu2 are called mass eigenstate. It is a hypothetical eigenstate. So there is a rotation. Okay. In one way, the flavor eigenstate is the mixture of the weak eigenstate. Okay. So when it travels, they pick up a pace, and this is responsible for the neutrino oscillation. This is the formula of the probability of neutrino oscillation from electron neutrino to muon neutrino. It depends on angle. It is called solar angle, and it depends on the difference between length from source to observer. It is the mass square difference between m2 square minus m1 square. It is the energy of the neutrino released from the source. This is for atmospheric neutrino, from muon neutrino to tau neutrino. And so it is the angle, atmospheric angle. It is the m3 square minus m1 square. It is the energy of the atmospheric neutrino. It is the distance. So this formula is very important formula. It is a derivation. So I won't speak much about. So this is the it is a Nature, in the Nature publication. When the electron neutrino oscillate, at some point of time it becomes the muon neutrino because it is composed of Nu1 and Nu2. So with time the composition will change. So it becomes Nu2. So it is from the source. It is from observer. It is the neutrino oscillation. Okay. In the neutrino oscillation, we have three angles. It is the first generation, 1 and 2. It is the solar. It is the atmospheric. It is called the reactor angle. This is very small. This is why if we neglect this one, it is almost zero. This is delta is called the Dirac phase. It gives you CP violation. If delta is different from 0 and pi, it is called CP violation. Recently in 2012, 2020, K2K, in Japan, there is evidence of the CP violation, but it will be repeated again. Okay. So CP violation in neutrino sector because delta is different from 0 and pi. Okay. So this is the eigenstate. With eigenstate, it is the mass eigenstate. It is the three angle. It is the Dirac CP. If the neutrinos Majorana, it is called the Majorana phases. Okay. So but we have in neutrino 9 M1, M2, M3, the mass, 3 mixing angle, 1 phase, Dirac phase, 2 Majorana phase. These are observable, and you know, absolute neutrino mass, we had tritium beta decay, neutrinoless double beta decay, cosmology, the absolute neutrino masses can be measured from these three also. So these are the experimental things. This is a brief idea how neutrino masses are observed. It is the kinematical test, cartoon, and it is the cosmological WAP, and it is the neutrino oscillation, it is the double beta decay. In the neutrino oscillation, artificial source, natural source. In artificial source, accelerator, fusion, neutrino beam. In the natural force, solar and atmosphere, long baseline and the short base. All the neutrino experiment will fall inside this bit. So I don't have much time. So now, finally, what I want to say is that in superconductor, so atmospheric neutrino oscillation was observed and confirmed by using water detector, pure water detector. Okay, pure water detector, and in atmospheric. So atmospheric neutrino is, so it depends on the zenith angle. It depends on the zenith angle it was exhibited. Okay, and this is the cosmic ray. So this was observed. This is the cosmic ray, how neutrinos were produced. Okay, so this is a zenith angle dependence. So they have observed. It is the superconductor observation. I won't speak much about. So it means that from superconductor we conclude that muon neutrinos change to tau neutrino, and these are the measurements. The mass square difference m3 square minus m2 square is about this, in this range, and the mixing angle between these is range. So it was confirmed later on by many others also. So it was directly confirmed by Opera and the others, K2K, Minos, T2K, and that is IQ. Okay, so they were given the Nobel Prize. In the case of the solar neutrino, as I told you, 4 proton max inside it is nuclear fusion. Fusion means inside the sun. Okay, about 27 MeV is produced. Okay, so I won't speak much about. There are 4 reactions inside the sun. Okay, so in the case of the snow, we cannot use snow means Sudbury Neutrino Observatory. So that Harvard was seen proposed that we cannot use pure water as a detector in order to identify that where the neutrino has gone. Okay, so in order to find out where the neutrino has gone, in which neutrino it has been rotated, we have to use the heavy water. So use of heavy water in snow was first proposed by this Shane, but after this proposition, he published a paper in PRL and he died, and it was later on introduced. Okay, so using the heavy water, we have 3 reactions: charge current reaction, neutral current reaction, elastic scattering. If we use pure water, we have only elastic scattering, but if we use heavy water, we have neutral current, CC, and elastic scattering. So if we use heavy water detector, we can find out muon neutrino deficit from where it has been oscillated. It is found that it has been oscillated to tau neutrino. So electron neutrino has been oscillated to muon neutrino. It has been found with this heavy water detector in snow. So I am giving you all this reaction. Those people who are interested can these are the different reaction. Okay, different reaction. So this is the snow. So okay. So what I want to say is that so now this is a new. There are so many new experiments. Okay, One is hyper Kamiokanda in Japan. Super Kamiokanda will be upgraded to hyper super Kamiokanda in Japan. So this is thing. Now, what I want to say is that these are unsolved problems. Even though we measure the mass square difference of the neutrino, we don't know the masses, individual masses, M1, M2, M3. So M1, M2, M3, the absolute neutrino masses, we don't know. So this is one problem pending. If M2 is always greater than M1. So M3 is greater than M2, M2 is greater than M1, it is called normal ordering. And it is also possible that M3 is the smallest, M2 is greater than M3. This is also possible, it is called inverted hierarchy. For the same mass square difference, we have two possibilities. So we have to find out the mass ordering or mass hierarchy. So this we don't know. We have to find out the CP violation in neutrino sector also. We have to find out neutrino is Dirac particle, which is different from particle and antiparticle, and a Majorana particle or self-conjugate particle, which is equivalent to its antiparticle. And there is some experiment called LSND and others. They find that not more than three varieties of neutrino they have indicated that. So that is called sterile neutrino. From CERN experiment, only 3 neutrino varieties are possible. So sterile neutrino is extra neutrino which do not have interaction with WZ boson. We call sterile neutrino. Existence of sterile neutrino, 4th or 5th or 6th varieties of neutrino. It is the present experimental things. Okay. Now,
time.
Oh yes. Now I am finishing now.
Okay.
Okay. Let me complete. Yes. Let me complete last line. In India also we have one experiment called India-based neutrino observatory INO. So we are trying to catch up and compete the entire world also. It is INO. So it is in near Madurai, Bodhi West Hill, and India-based neutrino. It is muon neutrino. Okay, so those interested people, please find out. So if we are lucky, we can find out some of these some pending problem in neutrino. So these are the agenda of INO neutrino. We want to find out atmospheric neutrino, hierarchical CP violation, and many other things. Okay, okay. So lastly, I want to point out this picture because Emperor's New Clothes. This means that young people, unlike me, young researchers, young people should have a gut to question the existing theory. Okay. So they should be able to question the existing theory, whether it is right or wrong. Only then new science will come up. So this picture is very famous. I borrowed it from Sergeant Nalikar's paper. Okay, thank you very much. Okay, I could not present up to the satisfaction. Time constraint. Thank you very much once again. Okay.
Thank you, Professor Nimai. Thank you for your illuminating lecture on neutrino oscillations. And yes, that's why I told the people here think differently. Yeah, that's how the solution to the problems comes. It is a very hot topic nowadays, the neutrino oscillations, and you have it cannot be done within a time slot of half an hour. You need more time, I understand. So far as these neutrino oscillations are concerned, does it make possible these neutrino as a candidate for the dark matter?
People are thinking of, but still there is no, still it is possible, but still but neutralino in supersymmetric particle, is the axion and neutralino are the candidate. But neutrino, it is rule out nowadays. Slowly rule out neutrino. Hello, sir.
Okay.
But supersymmetric particle called neutralino and axions are strong candidates for dark matter at the present.
Okay. I open the session for the discussion. Any question from the audience?
Okay, I will send my transparencies and you please study, okay, in detail. Okay.
Thank you.
Okay. Please distribute my transparencies to all the.
We have recorded your lecture, so we will distribute this lecture. Yeah.
Thank you very much.
Thank you, Professor Nimai, for your illuminating lecture. Thank you very much, and we hope more contribution, more collaboration later on also. So we thank you, Professor Nimai, and now I invite Professor. Just a minute. Professor Durgesh Rai. Professor Durgesh Rai, can you listen me? Professor Durgesh Rai. Professor Durgesh Rai, can you listen me? Are you in the conference? Hello? Hello?
Hello.
Am I audible? Professor Durgesh Rai. Yes. There is light humming coming in your mic. Eh? Professor Durgesh Rai, can you listen me? Yes, Professor Durgesh Rai is with us, and so our next speaker will be Professor Durgesh Rai. Let me introduce Professor Durgesh Rai. He has done his post-graduation from Banaras Hindu University. He comes from the solid state physics, condensed matter physics, and he joined later on. He joined IIT Kanpur, and he did his MTech from IIT Kanpur. He later on moved to United States for his PhD, and he got it there from the University of Cincinnati, from Department of Chemical and Material Engineering.
Hello.
Am I audible?
Yep. Yes, you are.
So he did his PhD from United States University of Cincinnati, and from Department of Chemical and Material Engineering. He had been postdoc at Oak Ridge National Lab at MIT, Massachusetts Institute of Technology, and he was a senior scientist in Oxfordshire in United Kingdom. His work is on X-ray and neutron scattering, and today he'll be talking about his work is on X-ray and neutron scattering, and today he'll be talking about a glimpse of fundamental and applied physics aided technologies for current and future health research. So this has something to do with the health research, and in the era of corona pandemic, this lecture seems to be a very useful lecture. Yeah? Professor Durgesh Rai, can you please start your deliberation?
Okay, can you see my screen?
Yeah, we can, yeah.
Right.
We can.
All right. So I will try to manage it within half an hour. That's my goal. We'll see how far I can go.
Okay, that's right. Yeah, thank you.
Okay. So the idea here is that I wanted to, as you correctly stated, a glimpse of how modern technologies come together to help with fundamental research in healthcare physics. My training is in physics, so I see things as a physicist. And I want to present two aspects. First, how instrumentation is approached from basic principles of physics. What are the challenges of first principle physics in, when it comes to industry for 24/7 operation, how you actually deal with that, how you optimize instrumentation for that kind of an operation. And I'll give some glimpse of basic biophysics, again, suitable for physicists for most of it. And then the idea is that I'll actually shift gears towards some imaging. I'll show you how it is done. And then the idea is I'll give, at least if not by slides, I'll basically try to tell you how modern technologies and progress in image processing is going to be very helpful. We all have, for example, our Android phones. They all are very good at image processing. So
Durgesh, Dr. Durgesh, please unmute yourself.
You are muted, Professor Durgesh. You are muted. Please unmute.
Durgesh, unmute. Dr. Durgesh, please unmute yourself.
Professor Durgesh, you please unmute your mic. Yeah? It's muted. Professor Durgesh, can you please unmute your mic?
तो अगर जब
Professor Durgesh, can you please unmute your mic?
तो अगर जब इसी जैसे मानो मैं अपना ऑडियो खोलूंगा ना तो मेरा भी सुनाई देगा ना.
Dr. Durgesh, please unmute your mic. Dr. Durgesh, can you please unmute? Your audio is not coming here. Hello. Dr. Durgesh, please unmute your mic.
someone please call him on his phone, on his mobile. Someone please call him.
Okay.
How about that?
Call him.
Now, can you hear me?
Now
Yeah.
it is
Can you get-
working.
Now you are audible. Yeah, you are muted. Now it's on.
It
Yeah.
is working.
Now you are audible. Yeah, you are muted. Now it's audible.
Okay, so I'll repeat everything I said. All right. But you can see my shit. But you can see my screen, yeah?
Yeah. We can. Yeah.
Oh man. Well, let me reiterate what I was saying. So the idea behind the talk is that I want to give you a glimpse of fundamental research that is being done using applied physics in the healthcare research. I intend, here's the layout. In the interest of time, I'm going to talk mostly about how do we optimize high-process SAC cell, and then I'll try to integrate a glimpse of a couple of approaches for COVID research in the perspective. I'll then go and talk about machine learning algorithms on the go. So, and it has all to do with how it's implemented by a matrix process. And if time persists, I will elaborate more on the on how neutrons and imaging actually can couple together with other instrumentations and learning algorithms, machine learning, and hopefully deep learning down the road, to predict different problems in health, and use to diagnose them. So with that, I'll give you a very brief understanding that the whole purpose here behind this talk would be to elaborate how instrumentation suits are going to be made, for example, for neutrons, which will depend on neutron characteristics and optics, sample environment, and detector geometries all coming together to present a perfect instrument for a particular problem. I do not foresee that I will have the time to elaborate on the problems, but I will give if I don't have this time, I'll just give a very brief overview of where we are going. And it is important to understand that the whole X-ray, no matter how capable your instruments are, if you don't have the right user base which can complement your resources, it doesn't really works to the magnitude it could. So we are looking into that direction as well, that how we can use computational as well as complementary techniques to better showcase the capabilities at neutron and synchrotron sources. So I will discuss a little bit about high pressure biology. As a physicist, physics pressure is very important to me, because you must have heard of temperature, denaturation, and all kinds of physics. But pressure is not done largely because of problems with instrumentation. They're just not available in the world. They're kind of very difficult. So that's the problem we are trying to solve. And even if you actually build an instrument, it has to be user-friendly. Until you actually make it user-friendly, your capabilities do not really matter. So before that, I will briefly introduce you to why we do this. So life actually exists under pressure a lot. There are deep sea hydrothermal vents, couple kilometers deep, where sunlight doesn't reaches, but there is very active life. The Pacific viper fish, they go 5 kilometers. And then I'm sure you might have heard of microanimal called tardigrades, which can survive 60-kilometer deep water, which doesn't even exist, but 6 kilobar pressure. It actually exists in space without, under radiation conditions, very low temperatures, and it's very difficult to kill. So we'd like to understand how these things work, and then it's all about also the origins of life, the limits of life. There are lots of biophysical problems to be solved. To provide those which do not have a background in biology, like myself, let me give you a very simple example. Is that proteins are like, you make your hand, okay? You have like 5 fingers, you actually make a fist, and that's how proteins are. Basically, they're a combination of, they're like your fist, consisting of your palm and 5 fingers. If you notice your fist, you'll notice that there are curvatures on it. And in fact, if you actually have some sand and you put it inside your fist, you will see you will be able to capture some even when you actually close it all the way. And that is because there are cavities inside our fist. And the same way, proteins have those as well. And they're very essential. The same way, proteins have those as well. And they're very essential. They are very essential for enzymatic reactions. They are hydrophobic regions, and typically they're very essential for human existence. And so it so happens, at least under pressure, is that you have these cavities, you apply pressure, and then the water kind of goes into these cavities and it unfolds. If you notice, that you might come to the sense that the water actually goes into the hydrophobic regions. All right. Now, if you heat this in protein, the interaction with water with the protein actually happens in the hydrophilic areas on the surface, for example, as you can see in the image. On the other hand, the pressure actually affects the hydrophobic regions. So, in a lot of ways, they are very complementary in nature. Nonetheless, should give you some basic ideas of how it works. Let me give you an example of a COVID research that actually is being done going into tomorrow, day after tomorrow, at our beamline. So it's called glutaminase GAC, if it's or GAL, depending upon if it's from liver or cancer. So this is a very common cancer-related protein that has been widely studied. If you notice, the inhibitors are right in the center, um, uh, and if it's actually a tetramer. This is basically 4 proteins stacked together in a way, and there is gap right in the center, and that's where all the reactions actually happen. If you actually apply, look into calculate the empty volume, you will actually quickly realize that this red, blue, and green actually denote 3 of the largest cavities inside this particular protein. So that kind of shows you how critical pressure is. You actually apply pressure and you can actually modulate the experiments that are going to happen tonight, not tonight, then certainly tomorrow and after tomorrow. It's our actually synchrotron is open for COVID related research. So with that introduction, let me also show that this is not new. It has been already been proved that using pressure you can actually change the activity of virus, because virus actually, if you look into their structure, they have a lot of them to basically already been proved. It has not been widely used, but this is the kind of approach we are taking. One approach is using the GAC. The other approach is directly on inactivating the virus. If you look into author list, there is this guy, Gerson Silva. Gerson is in Brazil. Recently, I actually had to get his. I had interactions, and he actually suffered from COVID himself. So he's also prospectively looking into a proposal in this direction. Anyway, so with that, I'll shift gears and show what we do with the small angle scattering. So in small angle, we could have light, you could have neutrons, you could have X-rays, whatever, you basically need a beam or a wave. You actually shine your sample. When you shine it on your sample, it will scatter because it will interact with the sample. It so happens that the angle we call reduced angle is denoted by a wave vector. Essentially, the wave vector is to normalize a geometry, because you can have different distances, but the wave vector Q can normalize all kinds of geometries. You can compare Q directly. If you calculate theta, for example, that we are generally used, intensity versus theta, that depends on the wavelength. But if you actually plot as a function of Q, it's independent of vacuum and, for that matter, any geometry. So that's what we generally use in small angle scattering. Most of people are, very familiar with what we call XRD, X-ray diffraction, which is at the higher angles, structure factor, interatomic structure correlations. Small angle generally happens in much lower Q at much smaller angles. And in the low Q, we look for what we call form factor, or the shape of the molecules more than the interactions between those molecules. Although in principle, we can actually look at those interactions as well, but that's a different story. We typically look at form factor. Um, the most important thing is to get well, but that's a different story. We typically look at form factor. Um, the most important thing is to get the size from RG, as you can see in the curvature, and look at how dense the whole aggregate is. It's very good in biology, at least it's very good for efficient for flexible peptides. You can acquire data in a matter of seconds. It's very economical, and you can look at tertiary structures and then complement with secondary structures from, let's say, any spectroscopic methods, IR, or any spectroscopy for that matter. With that background, I'm going to go directly into the instrumentation part of high pressure design. So the underlying principle is that it uses what we call Bridgman seal and by area. Okay, so you actually reduce the area using an O-ring. So as a result, the pressure on that O-ring becomes much higher than the area on the whole surface, and that is how O-rings work. In Bridgman seal, you basically use an O-ring with a backup ring. This is how the technical layout looks. You basically have three Bridgman seal. The X-ray goes through one window, comes out of the other window. Then the sample is changed from the top. Okay, and the whole hydrostatic pressure that's created inside is actually locked against this bolt lock mechanism that you can see, that you can slide in and out. This is how, if you actually keep this on sides and remove the main block, this is how it looks. What you should note is that you should note that the diamond, let's see.
Excuse me, sir.
Yes.
Kindly make screen visible.
Make things visible. It's kind. I'm sorry for that because
No.
Make this.
It is visible. You can check the design screen presentation by Durgesh Rai. It is visible, and you can pin your screen in that. Please, sir, continue.
Okay, sir.
Okay. Yeah, I'm sorry for, but it's kind of tricky to change in the middle for obvious reasons. So so the idea is that the way it works is the diamonds are actually seated on these two seats on either side, and in the initial design, which was very sound first principle physics design, the diamonds was pressed against the surface using two springs, metallic springs that you can see in sort of yellow in this figure. I don't know if you can see my cursor. And these two are then pressed against this blue spacer in the center. And this is fine for general lab purpose. But when you actually use on a synchrotron 24/7, or for that matter, any neutrons or industrial application, then things are going to go wrong. And when things are going to, it's sort of difficult to show in the figure. I don't think I am doing justice to the part, but let me show what the idea is. The idea is that instead of things, getting correlated, which is the pressure on the diamond is because they're both pressing against this spacer in the center. We actually designed ourselves or redesigned the seats in a way that each of these two sections on either side is basically an independent system. Okay, so this way you get the advantage that you basically have your seat, your O-ring, the diamond which is shown in black. It should certainly have been shown in white, but then white against white you can't see. So So the thing that is black is the diamond. And what this enables us is that it enables us a modular configuration. And what I mean by that is that if there is anything that goes wrong in one side, you just kind of swap it, instead of having to redo the whole assembly. Thereafter, this is how it looks. We actually put some pocket on the outside. So what this enables us to do is that it actually enables us to put vacuum and further optimize our background. We then worked on enhancing our mechanical stability to make sure that we have better positional and predictability. This is again very important. Biological samples, organic samples are not great at scattering. Okay? We are kind of carbon. So anyone who has done, EM and EM know that organic matters are not great for contrast using, for that matter, any most techniques. So us being carbon and like plastics mean that we have to be very efficient to get good data statistics. So then we came up with particular set of stages, low profile stages that provided extra stability, thermal jackets that's great for temperature equilibration. And in addition to that, we were able to get a vacuum line operational, and this actually mates to the vacuum. And then that is something that I'll show in the next slide. And this was very stable throughout the operation. We didn't see much issues with reproducibility of our data. Then the next thing is that everything works. Now let's optimize the path length. Okay, what do we need for that? We need just the right thickness of diamond windows. The thicker you get, the more is your background. So you want to actually optimize your background as much as possible, which we did using a special kind of diamond called HPHT, high pressure, high temperature diamond, sourced from Russia. Then we optimize what we call attenuation length, which is basically as X-rays travel through your medium, they get absorbed. So you just need the right, to get the best statistics, your attenuation length should be equal to your path length, and that both equal to 1 by E, which is so we can match that. And lastly is the transmission. So we actually calculated the transmission for the whole setup, and we optimize these 3 configurations to get the best statistics, and that I'll come later. This is how it looks on the beamline. You basically have detector, Eiger 4M detector, and then this cell, which we use a couple of transducers to measure it. And then, this looks fancy, but what it says is this is how it looks on the beamline. We have everything automated, and you can actually get your data from the comfort of your data acquisition room. Because we did, we did this experiment under different pressure as such, the contrast actually decreases, and that's why you see a reduction in the contrast. A lot of people in biology